I'm mostly going to be using the language of just geometry today. So if for some of you, I know may prefer the algebra, but yeah, just let me know if you are confused. Okay, so the title of my talk is Information Encoding Methods, just like, to be simple. And so really I'm going to talk about the method of encoding the geometric frustration in tetrahedral packing with these 4 methods: gaps or curvature, distortion, or twisting. So Clea already mentioned a little bit about that. So geometric frustration is more like in material science, like all soft matter polyhedron packing and all that. So, but here, because we're talking about math and physics, so that's why I changed the geometric frustration to information. Okay, so I'll explain later why. And so first, what is geometric frustration? How many of you heard about that? Yeah, so it's Riemannina has a paper on geometric frustration. So it's talking about in tetrahedron packing, because of the irrational dihedral angle of the tetrahedron, if you put 5 in a circular fashion, and so because the dihedral angle is 72.5, so it will not close the circle. It's a little bit, there will be a little gap there. And similarly, if you put 20 of them around the point, also it's not going to close this whole, volume, so there will be gaps. And so that is kind of a frustrated. And also because in this way, if you put 5 tetrahedron, like 5-fold symmetry, and it's kind of impossible for the local symmetry to propagate, the 5-fold symmetry to propagate. So that is like a definition of a geometric frustration. So then how are we going to deal with this? This is defined as geometric frustration, but it can also be used as an information, right? So if you have a crystal that is periodically packed, so there is not much of information there really. But if there is something like this, then we can actually treat this as the information, and then try to encode it, and either by curvature, or by twisting, which is the angles, or we can use distortion. We can distort the edges, right, to make it irregular, or we just leave it as it is, like with gaps. Okay. So, and then in all 4 methods, by the way, we could actually achieve the propagation of the local symmetry, like which form a quasi-crystal. Right, so I'm trying to use the 5 tetrahedron around sharing one edge to illustrate these 4 methods. So first I wanted to point out the key to manipulate the dihedral angle to become 72 degrees, right? 2 pi over 5 around this central plane. By central plane, I mean if this is a 5 tetrahedron, the central plane means that the plane that would be perpendicular to the shared edge, and also it will pass through the center point of the edge. So let's define that's a central plane. And so, yeah, so then if we in some way can make this angle right now on the central plane, like right, each tetrahedron, if we plot out the cross section crossing this central plane, we can see there will be a 72.5 here, 72.5 here, and 72.5 on these places, and there will be little tiny gap angles there. So then how are we gonna actually manipulate that 70.5, and so 70.5, become 72. So then this whole circle gonna be closed, right? So there won't be no gaps. So the first thing, so here is with gap, right? So use the gap to kind of encode that kind of information there. And then the second method is by twisting. So I have a model here, like you kind of twist each tetrahedron, like rotate each tetrahedron around an axis that goes through the midpoint of the sharing edge and then the midpoint of this edge. So just twist them this way or the other way. Depending on which way you twist it, you can get a left twisted or right twisted 5 group. So then by doing this, and then you can see all the gaps disappeared. And if you really like draw this central plane, you could see that the dihedral angle 17.5 is like an angle that is, if this is a plane, and the angle is no longer in the plane, the angle is like one of the edge coming this way, the other edge coming this way. And so these angles like this, and then the projection of this angle on the plane is actually bigger. So it's a 72 degree. So you can maybe pass it to see it's a 5 group. So then that's one way of encoding the information. And another way is by distortion. So literally, we just shorten these edges, these edges, these top and bottom edges, and then to make them close here. So this is what we achieved here. So, and these tetrahedra are no longer regular. This is first way, second way, third way. And then another way of removing these gaps is to curve it. It's like maybe I can show this. It's like here, like if you have these triangles, right? And they have pentagonal symmetry. So, and there are gaps around them. So, but you could fold them into an extra dimension. Like here, you fold them down like this, and then the gaps will be closed. So this method, we call it discrete curvature, because the discrete curvature actually means like everywhere is flat except right here when these two flat space kind of joint. So there's curvature there. So that's it's kind of like, it's difficult for me to draw the 4-dimensional thing, So just imagine all 5 tetrahedron bent into the 4th dimension to close up the gap. So that's all the method. And then so in all these 4 methods, basically we're trying to kind of on the central plane try to close up these dihedral angle. I mean these angles that is either the dihedral angle or we call it the effective dihedral angle. Okay, so those are talking about the clusters that are around an edge, and then the next is the cluster around a vertex. So this is the gap case, around a vertex you can have 20 tetrahedron, and then you can have these gaps equally distributed. Okay, so 20 group, right? This is a 20 tetrahedron sharing one vertex, and one way to close up the gaps is by twisting these tetrahedron, and the twisting angle is a jitterbug angle. If you guys, any of you heard about the jitterbug transformation? Yeah, so it's like when you rotate the triangle to transform from icosahedron to cuboctahedron, or from cuboctahedron to icosahedron. It's the angle. Okay, so then, this is by twisting, and then this is by if you curve each tetrahedron into the 4th dimension, just like when you curve these into the 3rd dimension. And so you will close up the gap as well. So this is, if you guys know the 600 cell around the one vertex, there are 20 tetrahedron, right? 20 regular tetrahedron. And that configure like this. Like each tetrahedron corresponds to the other one, bent just a little bit. The bending angle between the tetrahedron or dihedral angle is also the 15.5 degree, which is the angle that between this face and this face, the relative angle. yeah, and that is by distortion, which is simple. It's just like since the regular does not have the space, you just make the irregular, just to shrink the inner edges, and so they make these meet, and then, yeah. So that would also, that's another method. So gaps, twisting, that's by discrete curvature, and that's by distortion. So 4 methods.
And in all 4 methods, it's a golden ratio expression. So the edge contraction is the golden ratio edge contraction, same with the rotation into 4D, same with the rotation in 3D.
Yeah. So I wanted to point out that the transformation between the gap and the distortion, I mean the twisting, right? So we know it's through a rotation of the tetrahedron. We rotate each tetrahedron, we get this. And that rotation is a jitterbug angle, which is 22.2. You know, it's an irrational angle. Just that's, I call it the transformation angle. And after the transformation, and there is an angle between these 2 tetrahedron. And you can see this is the relative rotation. This angle is the relative rotation. And that is a 15.5. So we call that angle P, we call the transformation J. So remember, there is a transformation angle for this transformation, and there is an angle, we call it a joint angle. Because this is one part, this is another part. The angle between them, I call it the joint angle, okay? So there's a joint angle 15.5, there's transformation angle 22.2. So similarly, from the gap to there, okay, you have to bend each tetrahedron, right? Bend it down or bend it up. And this angle that you rotate the tetrahedron to bend it up or down, right? So that angle, I call it the transformation angle. It is the angle for this transformation. And the angle is also 22.2, which is equal to this transformation angle. So after the transformation, right, and then the tetrahedron, between tetrahedron, there is a little angle there, because after you bend this is the bending angle, right, from flat there. This is the bending angle, that's 22.2. After you bend all the tetrahedron, and the tetrahedron are no longer having, you know, each tetrahedron is a space, 3 space. Originally, they live in the same 3 space. Now there is the angle between the 3 space. And that angle is also a joint angle, right? It's an angle that is a fixed, it's a not transformation angle. That is also 15.5. So just remember, from the gap to the twisting and from the gap to the discrete curvature, there is interesting kind of phenomena there. They have the same transformation angle, and they have the same resulting joint angles. And how is that? Is that just a coincidence? So that's what I'm going to talk about. Okay, so these are just some calculations, you know, like to calculate when we bend the tetrahedron to 4D, and that's the angle to bend it to 4D. And after that, there is an angle between the tetrahedron, which is the dihedral angle of the 600 cell, and which is this angle. This is the 15.5 angle. This is 22.2 angle. And so, here I'm trying to argue, because we're trying to, our targeted dihedral angle is 2 pi over 5 to close up, you know, the gaps. And so I'm trying to argue that because cosine in J is a transformation angle, and this transformation angle equal to tangent, this is the real dihedral angle, and this is the effective dihedral angle, which is the 72 degree, right? So because of this relationship, and that is why this transformation angle made it possible that for the gap to close when you do the kind of curvature, right? So that transformation, which is a curvature. And this exactly the same thing happened here when we try to twist it. When we try to twist it, and we notice that the transformation angle, the relationship between the transformation angle, the effective dihedral angle, and then the real dihedral angle also has the same kind of relationship. That's why these 2 transformation angles are the same. And I didn't actually from here, I didn't go on and prove why the joint angle, the resulting joint angle are the same. But in the paper, we have like a very detailed proof using Clifford algebra method by Richard. So I did it this way, just like trigonometry, and then so he did it use Clifford algebra. And so, and then this is just one case, right? Like around one tetrahedron, there are 5, around one edge, 5 tetrahedron, around one vertex, 20 tetrahedron. So it seems like whether we use the discrete curvature or we use the twist, there is like this kind of a magical matching between these angles, the transformation angle and the joint angle. So is this like a coincidence and this just happened in this one case? So that's why I went on look at the other cases. Okay, so we can see like, okay, so this is what we have talked about this. We have discussed this. So this is the evenly spaced edge sharing group. They're sharing, these 5 tetrahedrons share one edge, and there's little gaps. And so we can just twist each one, has this angle, twisting it to close up this 5 group. And this is the vertex sharing group, And so the transformation angle I'm talking about is for the vertex sharing. So this is the transformation angle, which is 22.2, and this is and this angle between the tetrahedron facets are 15.5. And so you can see the 5 group and 20 group are related in this way. So that's the top tetrahedron. This is still 20 tetrahedron. This is 20 tetrahedron. So if we extend that face, double the edge length, and also there is a one bottom one that will also double its edge length, and then become a one big giant tetrahedron. And so similarly, we can get the other 4. So you can see the 5 group and 20 group are actually, inscribed in each other in this way. So then, here is, okay, so in a twisting case, we have the angle, and this is the edge angle, meaning like when they share one edge, the twisting angle is this number. And then when they share one vertex, and the twisting angle, which is the transformation angle, is this angle. And then this is the F means the face angle, the angle between the facets, which is the joint angle, is this one, which is 15.5. This is 22.2.
So yes, the last drawing as a subset of the 20 groups. So you show us that we can see the 3 different symmetries. The threefold is in the 20 group at the left. The fourfold.
Well, I haven't talked about this yet.
Yes, but we see the 20 group is in orange in the middle. Yes.
Yeah.
Yes.
Yeah, this is 20 group.
And another remark, just the second line, edge sharing. This is just a little confusing because in fact the edge is not shared, it's the mid-edge vertex which is shared.
Yeah, well, it started with the edge sharing, yeah. So anyway, so this is the twisted case, and then we know that the curvature case, when you curve them up, it is a part of a 600 cell, right? Because for 600 cell, in 600 cell, around each edge you can find 5 tetrahedron. And around each vertex, you can find 20 tetrahedron. And they're curved. The tetrahedron, like between each tetrahedron, there is a like a bending angle. So exactly the same as how you would bend, these tetrahedron. You would bend these tetrahedron to close up the gaps. So what we have, when we use the discrete curvature method, basically we just get a vertex configuration in a 600 cell. So then we're talking about, what about like we, instead of 5 tetrahedron, we arrange 4 tetrahedron around the vertex. And so this is what we got. We can similarly twist each tetrahedron. We just need to twist it more. So they become a 4 group. You can see now their faces are touching again. And so around each vertex, we can have 4 tetrahedron. We can have 8 tetrahedron actually around each vertex. And so they would be arranged like this. So this is, and these are the vertex clusters, for fourfold symmetry. And so this is to overlap the vertex sharing and the edge sharing together. And this is what you can see. The edge sharing, I made it a little bit large so you can see the relationships. And so the last figure is, I wanted to put the 4 group, overlap with the 20 group, which is this case. So you can see these cyan tetrahedron, they're part of this vertex sharing fourfold symmetry clusters. And these yellow ones are the edge sharing fourfold clusters. So you can see they overlap like this. That is why in the 5 case, I don't have another way of doing it because, it's just itself. The 20 group is itself. And now I'm trying to put the 3-fold and 4-fold all to compare with the 5-fold case. So, and then so this is a 4-fold case, and for 3-fold case, similarly, we also twist each tetrahedrons to make them close up the gaps like this. And then so if we look at the vertex sharing case, it looks like these 4 tetrahedron there. And you can see the relationships with the edge sharing. So if you look at each 3, they can form a 3-group edge sharing pair. You can look from all different, 4 different angles. And then yeah.
I have another question about this, the last line.
Yeah.
So it's clear that on the right, the size of the tetrahedron from the 20 group is half of the size of the tetrahedron from the 5 group. But on the 2 other, it's not clear. It looks like the ratio is different.
No, it's the same.
It's also
double.
1 to 2?
Double, yeah.
Okay.
Yes. And so anyway, so these 3, vertex sharing cluster is also a subset of the 20 group. And then also these edge sharing 3 group also can be mapped like this. They share kind of like faces and edges. So yeah, so basically the 20 group has 5-fold there, 5 group there, and it has 4 group tetrahedron there too, and it also has this kind of 3-fold clusters in it. Basically the 3, 4, and 5 are all subsets of this 20 group. Okay, so the interesting thing is we already said that in the 5-fold case, right? No matter I said it's a 4-dimensional analog is a 600 cell because the 600 cell also has 5 tetrahedron sharing edge, 20 tetrahedron sharing vertex, and then that's the discrete curvature case for the 5-fold to close up the gap, right? And so then for 4-fold, its corresponding analog in 4D is a 16 cell. So if you know for 16 cell, around each edge, there are 4 tetrahedron. And around each vertex, there are 8 tetrahedron. So if we would curve, bend the tetrahedron in 3D case with the gap into 4 dimension, and then we would get a part of a vertex configuration of the 16 cell. And if we would do the 3-fold case, and so it corresponds to a 5 cell. So the pentachoron. So, for pentachoron, around each edge, you have 3 tetrahedron, and around each vertex, you have 4. So that's why. Also, the most interesting case is like the transformation angle are also the same in the 4-fold and 3-fold case. Because for the 4-fold case, the transformation angle is like pi over 3. And similarly, to bend these tetrahedron, these 8 tetrahedron into 40 to close up, it also needs, the bending angle is also pi over 3. And then the dihedral angle in the 16 cell is 2 pi over 3. And also the relative phase angle between these, the twisting case is also 2 pi over 3. And then 3-fold case also. The transformation angle here for the twisting transformation is this I forgot, oh, this is also the 22.2 angle. And then similarly in the 5-cell, the transformation angle is also this angle, and then here the phase angle is 75.5, and then in the 5-cell, the dihedral angle between the tetrahedron, right? Because the pentachron has the tetrahedron facets, so dihedral angle between the tetrahedron are also this angle. So basically, no matter it's a 5-fold or 4-fold or 3-fold, like we find these angle matching between the twisting case and the discrete curvature case. They're not only matching with the transformation angle and also the joint angle, which is the resulting angle between the elements. So that kind of give us some clue, like the discrete curvature in 4D, if we're looking at tetrahedron, right? So the discrete curvature, is associated with these two kind of angles, and they can be equally described like using the twisting method in 3D, because using the twisting method, we also have the same transformation angle and also the joint angle. So maybe it can suggest in a way like, whatever the model that can be modeled with discrete curvature, we can actually, use the twisting to model the same thing. But because then we have assumptions, right? So the fundamental element has to be the regular tetrahedron.
So just so you guys can keep tracking the motivation, we have two musts in our assumptions here. We must use E8, and we must use non-deformable tetrahedra as the quantum of space-time. So you might say, but why don't you guys just use the E8 to 4D quasi-crystal? And the reason is because of this extra binary sign value. So when we represent the Elser-Sloan 4D quasi-crystal in 3D using this equivalent method of one quantum of curvature that comes in a plus and minus value, we think we're going to be able to have more tools in our toolbox to build something physically realistic.
Yeah, so for now, just kind of remember these kind of information, because when we project from higher dimension to lower dimension, there is distortion. So this distortion can be kind of modeled with discrete curvature. This distortion as information, can be modeled with discrete curvature, which is the traditional way, and it can also be modeled as the twisting. So if you can get that kind of information, then that's what this talk is about. And I explained why, because the transformation are equivalent in a way.